All right, today we're going to continue talking about torque. Now, we talked about torque before, and we said that a torque causes a twist or a turn. Okay, it causes an object to rotate. It causes an angular acceleration. All right, we've talked about the symbol before. It's the Greek letter tau. And we have an equation, okay? We said that torque is equal to the force times the distance times the sine of theta. However, we have some more equations, okay? We talked in the past about how some things that are related linearly and rotationally, okay? So we've got linear concepts, and then we've got some rotational concepts. All right, and we talked about how x, or displacement, which could be x or y or d, in rotational, that is theta, okay? And we talked about linear velocity, and we've also talked now about angular velocity. We talked about linear acceleration, and we've talked about angular acceleration. And we've talked about force, okay? Remember, a force that is not zero, a net force, causes a linear acceleration. Well, what causes an angular acceleration? It's not a force, because if you apply the force at the hinges, we know that it's not going to cause the object to rotate. What causes an angular acceleration is what we just wrote down. A net torque will cause an angular acceleration. Okay? Now, force was equal to mass times acceleration. That was Newton's second law. Okay? We are going to do a similar thing over here. We're going to use Newton's second law. A torque causes an angular acceleration, and it's equal to something times the angular acceleration. That something is whatever is similar to mass. Okay? Mass is the inertia of the object. It's how much its resistance to change linearly. Okay? It's how much it wants to stay at rest or stay moving once moving at a constant velocity. Similarly, we have moment of inertia, and we use the capital letter I in rotational motion. So Newton's second law here simply states that torque is equal to the moment of inertia multiplied by the angular acceleration. So that is our next equation. The net torque is equal to the moment of inertia times the angular acceleration. The units are still a Newton times a meter. Okay? It is a vector. Okay? And counterclockwise is positive. Okay, which means clockwise is negative. Some examples. Well, anytime we've got a twist or a turn. So every time we are opening doors, okay, we are causing a door to rotate, to twist or turn. If we open a bottle cap, so if we twist off a bottle cap, so you open up your water bottle, okay? Again, you could open a jar. All of these things are causing a twist or a turn. Similarly, you could simply just rotate your arm. So those are all examples of a torque.